Okay. So hi everyone, so good afternoon all. Okay, so first of all let me know whether audio and video everything is clear. Okay, so if it is not clear, please give some comment in chat box, right? Okay, so otherwise we will continue, right? Okay, so we are dealing with the subject electromagnetics. So in that we are dealing with the topic magnetostatics. So in that we have completed Lorentz force equation, and also we have completed Biot and Savart's law. We have seen the applications of Lorentz force equation, and also we have seen the applications of Biot and Savart's law, right? And also we have started with Ampere's law. Now we are studying about the applications of Ampere's law here. Okay, so what is the purpose of Ampere's law here? What is the purpose of Ampere's law? So the main purpose of Ampere's law is to determine what? Is to determine the B field due to a given uniform and symmetrical current distributions. Understood? Okay, so so we have seen how to determine the B field by applying what? By applying Ampere's law, and all these things we have seen, right? Okay, so in the previous session here, we have seen how to determine the B field outside the current carrying wire, and how to determine the B field inside the current carrying wire. Yes or no? So if I consider this as a current carrying wire which is carrying a uniform current, I is nothing but what here? I is nothing but uniform current here. So that means if I is uniform means current density J is also what? Current density J is also uniform. Understood? So we have considered a cylindrical wire of radius rho, and here in this cylindrical wire we have assumed that the current, a uniform current, is flowing throughout this cylindrical wire. So that uniform current we have considered as I. Now due to this current carrying wire, we try to determine the B field in all the regions, that is outside the wire and inside the wire. So these are the expressions we got here. These are the expressions we got, right? Okay, so this is the expression for B field for R greater than rho, that is outside the wire. And here if you substitute in place of I here, if you substitute J into pi rho square, J is nothing but what? J is nothing but current density here. J is nothing but current density. So J multiplied by what? J multiplied by this surface area. This surface area will give you what? Will give you this total current. So we can represent this total current as what? As a current density multiplied by what? Multiplied by surface area. Understood? That is J into pi rho square. So if I substitute in place of I, if I substitute J into pi rho square, then you are going to get the expression in terms of what? In terms of J. Okay, so here this is the expression in terms of what? In terms of I. So what you have to do here? Just replace I with what? J into pi rho square. Understood? Okay. Next, for R less than rho here, so what is the expression for B field we got? B field is equal to mu I R by 2 pi rho square. So this is in terms of I. So if you substitute in place of I, if you substitute J into pi rho square, then you are going to get the expression for B field in terms of what? In terms of J. Right? Okay, so these are the expressions we got, and also we have seen this graph here. Yes or no? So this region R less than rho represents inside the wire, and R greater than rho represents what? Outside the wire, and R equal to rho represents on the surface of the wire. Now if you observe inside the wire here, B is proportional to what? B is proportional to R. So that means the field is increasing linearly with respect to R inside the wire. So what is the reason also I have told here. So inside the wire, as the radius increases, radius of the loop increases, then the current enclosed by that loop will also going to increase, and hence the B field is going to increase linearly. So once you go out of the wire, then then B field is going to decay as what? B field is going to decay as 1 by R. Understood? Okay. Okay, so all these things we have seen here. So outside the wire it is inversely proportional to R, and inside the wire it is proportional to what? It is proportional to R, right? And where the field is maximum here, the B field is maximum on the surface of what? On the surface of the conductor, right? Okay, so these are the things we have seen in the previous session. So now okay, so now we try to solve this problem here. So this problem is given in gate. This question is given in gate, right? Okay, so we try to solve this problem here. So which is based on what? Which is based on, if you know all these things, then you can easily answer this gate question, right? Okay. Okay, see here, what is the question they have asked here? See, so an infinitely long uniform solid wire of radius A, an infinitely long uniform solid wire of radius A. So solid wire means you have to consider that it is a cylindrical wire of radius what? Of radius A, right? Okay. So carries a uniform DC current, of density Z bar. That means they have given the current density. And what they are saying here, this current density is what? Uniform current density. Understood? Okay. So then in the first question they are asking that the magnetic field at a distance r from the center of the wire is proportional to. So the magnetic field at a distance r from the center of the wire is proportional to. Okay. So that means they are asking that, so this is they have given some cylindrical wire of radius what? Of radius A. So instead of rho, you are having the radius as what? You are having the radius as A. That's what they have given. Okay. So now they are asking, so for this cylindrical wire, they are asking the magnetic field at a distance r from the center of the wire. See, from the center of the wire means what here? Sorry. See, from the center of the wire means what? From the axis of the wire. So that means r is measured from the axis of the wire. So that's what they mean. Center of the wire means. Understood? Okay. 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 So now they have given the options here. So in these options you have to identify the correct one. So now see here, in option A, what they have given here, the magnetic field at a distance r from the center of the wire is proportional to. Option A, they have given r for r less than A. Okay. That means in option A, they have given that B field, the magnetic field, is proportional to what? Is proportional to r for r less than A. So this is what they have given here. B field is proportional to r for r less than A, and here they have given that B field is proportional to what? B field is proportional to 1 by r square for what? For r greater than A. Okay. So this is option A here. Understood? In option A, what they have given, B field is proportional to what? Is proportional to r for r less than A, and it is 1 by r square for r greater than A. Understood? So is this correct or wrong here? We know that B field inside the wire, is inversely proportional to what? Sorry, B field outside the wire is inversely proportional to what? R, and it is directly proportional to what? R. Understood? Inside the wire, B field is proportional to R, whereas outside the wire, B field is inversely proportional to R. Understood? Okay. But here in option A, what they have given here? So they have given it is proportional to R for R less than A. So this one is correct here. It is proportional to R for R less than A. This one is correct. But here they have given 1 by R square for R greater than A. That means outside the wire, they have given that magnetic field is inversely proportional to what? R square. Okay. So this is wrong. Why here? Because B field outside the wire is inversely proportional to what? Is inversely proportional to R, but not R square. Right. Okay. So that means option A is what? Option A is wrong. Next, in option B, what they have given here? 0 for R less than A and 1 by R for R greater than A. So inside the wire, they are saying that B field is 0, which is wrong. Yes or no? And 1 by R for R greater than A, that is outside the wire, B field is inversely proportional to what? Inversely proportional to R. Okay. So that means this one is correct here. This one is correct, but this one is wrong. So overall, option B, we can mark it as wrong. Right. Next, option C here. So what they have given? Magnetic field is proportional to what? Is proportional to R for R less than A. So that means inside the wire, they have given that magnetic field is proportional to R. Next, outside the wire, that is for R greater than A, they have given magnetic field is proportional to what? Is proportional to 1 by R. Is proportional to 1 by R. Yes or no? So, and hence option C is what? Option C is correct. So, just remember this diagram here, just remember this diagram. Okay. So, this is B field, this is R. Just remember this diagram here. So, this is for R equal to what? Here the radius of the wire they have given as A. So, this region will be R greater than A. This region will be R less than A. So, inside the wire B is proportional to R. Outside the wire B is proportional to what? 1 by R. Okay. So, you just remember this diagram, then you can easily answer this question. Okay. So, option C is correct and option D. So, B field R less than A, for R less than A they have given magnetic field is equal to 0, which is wrong, and they have given outside the wire, that is for R greater than A they have given B field is proportional to 1 by R square. So, this is also wrong. So, that means option D is what? Option D is wrong. So, which one is correct here? Only option C is correct for the first question here, for the first question. Understood? Okay. Okay. Yeah. So, for the first question, only option C is correct, remaining all other options are wrong. Right? Okay. Yeah. So, next coming to the second question here, coming to the second question. So, this is linked answer type question here. So, that means the result of first one is going to depend upon what? Is going to this is not I think this is okay. So, this is common data here, not linked. So, this is common data for questions 1 and 2. So, this is common data questions for 1 and 2. Okay. So, this data will be same for what? For second question also, for second question also. Okay. Okay. So, you are having a long uniform solid wire of radius A carrying a DC current density of J bar. Okay. So, then so then in the second question what they are asking here, a hole of radius B, a hole of radius B where B is less than what? Where B is less than A is now drilled along the length of what? Along the length of the wire at a distance D, from the center of the wire as shown below. Okay. So, this is the figure they have given here. So, this is just a cross section of what? Cross section of the cylinder. See here, this is the cylindrical wire. You are having the cylindrical wire like this. Yes or no? Okay. So, here they have given the cross section here. Cross section is nothing but what? Cross section is nothing but circular cross section. So, this circular cross section they have given. Understood? Okay. So, actually, so this cylindrical wire is extending. So, maybe it will be like this here. Understood? Okay. So, I cannot draw that exactly, right. So, this is what? This is just they have given the cross section of what? Cross section of the cylindrical wire, right. Okay. So, they have given the cross section of the cylindrical wire here. So, what they are saying here is a hole of radius B where B is less than A. So, this is the hole here, this is the hole, a hole of radius B, which is what? Which is less than A, is now drilled along the length of what? Drilled along the length of the wire at a distance D, at a distance D from the center of what? From the center of the wire. So, let us say this is the center of the wire. So, at a distance D, from the center of the wire, you are having what? You are having a hole here. You are having a hole of radius what? Of radius B. Understood? Okay. So, what they have done here is you are having a cylindrical wire like this. You are having a cylindrical wire like this, right. You are having a cylindrical wire like this. So, it is carrying a current density, uniform current density of J. It is carrying a uniform current density of J. Understood? Now, what they have done here? So, they have drilled a hole here. They have drilled a hole somewhere here in the cylindrical wire. Okay. So, they have drilled a hole like this here along the cylindrical wire like this, right. So, this yellow color represents what? Represents the hole. Understood? Or I can say this is a cylindrical cavity. I can say this is what? This is cavity. I can say this is cylindrical cavity here, cylindrical cavity. So they have drilled a hole, they have drilled a hole, and made a cylindrical cavity at some location here. Understood? Now this cylindrical cavity, for this cylindrical cavity, I am considering this as what? This as axis. Now the distance, this is the center of the main cylindrical wire, and this is the center of what? This is the center of this cavity. Understood? So the distance from here to here, they have given as what? They have given as d. Understood? Okay, so the distance from here to here they have given as d. So that is the distance from this center to this center is how much here? Is nothing but d. Understood? Okay, so this is the circular cross section of the cylindrical wire here. This is the circular cross section of the cylindrical wire. Understood? Okay, so they have drilled a cavity at some location here, Understood? So the distance from this center and this center is how much here? D. Understood? So at a distance d from the center of this wire, they have drilled a cylindrical cavity or cylindrical hole like this. Understood? Now what they are asking here is the magnetic field inside the hole is, so that means at some point, let us say some point here, let us consider some point P, right? So let us consider some point P. So at this point P, so somewhere inside the cavity or inside the hole at some point P, they are asking what? They are asking the magnetic field. Inside what? Inside the hole or inside the cavity. Understood? Okay, so you are having a current carrying wire which is carrying a uniform current. Understood? So for that current carrying wire at a distance d, from the center of the wire, they have drilled what? They have drilled a cylindrical cavity or hole like this, or hole along this what? Along this cylindrical wire in this manner. Understood? Okay, so this top view here, I have drawn here. So the distance from here to here is d, and the radius of this cylindrical cavity is nothing but what? Is nothing but b. And the radius of this cylindrical wire, is how much here? Is nothing but a. Understood? So the radius of the cylindrical wire is a, and the radius of the cavity or hole is nothing but what? Is nothing but b, and the distance from the center of the cylindrical wire to the center of what? To the center of cavity is how much here? Is nothing but d. So now let us name this as O, and let us name this center as what? Let us name this center as O dash. Understood? So name this center as O and name this center as what? O dash. Right? Okay. Okay. Yeah. So now we have to determine the magnetic field inside the cavity here. Right? Okay. Okay. Yeah. So how we can solve this problem? See here. So just copy this one here. Okay. Okay. Yeah. Cannot be copied. Okay. Okay, I am considering here. Right. Okay, so inside the cavity at some point P, I want to determine the magnetic field. Understood? Okay. Okay. So here right. Okay. Let us consider this as z axis here, right? Okay, and this line is parallel to z axis. So this is the center of this wire and this is the center of this cavity. So the distance from here to here is d, right? Okay, so here the current density is z bar, current density is z bar. Okay. Now see here, so while dealing with Gauss law here, so we have seen similar type of problem here while dealing with Gauss law. So there we have taken a uniformly charged sphere, right? We have considered a uniformly charged sphere, and here at some distance from the center, we have made what? We have drilled a hole, or we have made a cavity, right? Okay, so of some radius, we have considered this radius as R2, and the radius of this bigger sphere we have considered as what? We have considered as R1, right? And here the charge is distributed throughout the volume of the sphere in this manner. Okay, so hope you remember this problem here. So for this one, we try to determine what? We try to determine the B field inside what? Inside the cavity at some point P, inside the cavity. Understood? Okay, so what we have done here, so they have given a uniformly charged sphere, and for that uniformly charged sphere at some distance d from the center, they have drilled what? They have drilled a hole. So that means here you are having what? Here you are having cavity. Understood? And we try to determine what? We try to determine the electric field inside what? Inside the cavity due to this charge distribution. So there what we have performed here? We have performed a superposition of what? Superposition of Gauss law. Yes or no? So what we have done there? So we have splitted this here. We have splitted this charge distribution into what? Into two charge distributions. Yes or no? So we have splitted this one into what? Into two charge distributions such that I can consider this as what? I have considered as a uniformly charged sphere, of radius what? Of radius R1. Okay, so we have splitted this into two spheres here, one is what? One is of radius R1, and another one is of what? Another one is of radius what? Another one is of radius R2. Another one is of radius R2, right? Okay, so here we have considered that this R2 is what? This R2 is a negative charge distribution. So this R2 We considered that it is having negative charge distribution such that here the charge density is how much here? Rho v, and it is what? And it is positive. And for this one, the charge density is what? Rho v, and it is what? And it is negative. And it is negative. So now, if you take this spherical charge distribution here, this is small R2 sphere. Okay, if you take this spherical charge distribution and keep it exactly at this location here, exactly at this location, then here you are having already rho v positive. Now you are placing this one here, so you are going to have rho v negative as well as what? Rho v positive. So rho v positive and rho v negative will get what? Will get cancelled, and hence you are going to have what? You are going to have in this region, you are going to have no charge. Understood? Okay, so that means here if you observe inside the cavity here, inside the cavity there is no charge, there is no charge. Charge inside the cavity is equal to what? Is equal to 0. So that's why we can represent this charge distribution in this manner here. I have splitted this into two spherical charge distributions such that here the charge density is what? Rho v, and for this one also what? Charge density is rho v, but here it is positive charge distribution and here it is what? Negative charge distribution. Now if you take this spherical charge distribution and keep it somewhere here at this location, then what will happen here? This plus rho v and this rho v negative will get what? Will get cancelled, and the net charge in this region, will become what? Will become 0. Will become 0. So that means this is equivalent to what? This is equivalent to this one. This is equivalent to this one. Understood? Okay. So there we have represented this point P. So this point P, if you observe, this point P is present inside what? Inside the sphere R1. So the somewhere here. Okay, so we have represented that point P and we have considered the distance from here to here as R1 bar, and we have represented this point P inside what? Inside R2. See, this point P is inside R1, inside sphere R1, as well as this point P is inside the sphere R2 also. Understood? So we have just represented that point somewhere here, and the distance from here to here we have considered as R2. Understood? Okay, next we know the electric field. Inside what? Inside a uniformly charged sphere. So we have substituted that expression and we have added these two. We got what? We got the net electric field at point P. Understood? Okay, so here what is the principle we have used here? We have used superposition of what? Superposition of Gauss law. Here we have used superposition of Gauss law. Understood? What we have done? We have splitted this charge distribution into two charge distributions. Then we try to determine the electric field at some point P, that is inside the cavity. So there, what is the result we got here? What is the result we got? So the result we got here is the electric field. The electric field inside the cavity is what? Is uniform, and it doesn't depend upon what? It doesn't depend upon either R1 or R2. It depends only upon what? It depends only upon the distance between the centers of the two spheres. So this one we have already studied here. Just I am revising all these things. Okay, why means this problem will be, can also be deal in the same manner. Here we are having charge distribution. Here what you are having? Current distribution. Understood? Here this is uniform charge distribution. Here you are having uniform current distribution. That's it. Understood? Okay. So the same procedure here, whatever we have followed here, so the same procedure we are going to follow in order to determine what? In order to determine the magnetic field inside what? Inside the cavity. Right? Okay. So please go through this problem here. I have already explained while explaining Gauss law. Understood? Okay. So if you would have attended this one, then it is going to be very, very simple. You can easily correlate these two. Right? Okay. So in the same manner here, see here. Okay. So in the same manner, see here, they have given a cylindrical wire of radius what? Of radius A, and at a distance d from the center of this cylindrical wire, they have made a cavity or hole. Okay, whose radius is what? Whose radius is B. Now they are asking to determine the magnetic field at some point P inside this cavity. So what I can do here is I can see here inside cavity, this is cavity here, yes or no? So inside cavity, what must be the current density here? What must be the current density inside the cavity? So inside the cavity here, inside cavity or hole, okay. So inside this hole there should not be what? There should not be any current, yes or no? So that means the current density inside, the net current density inside this cavity must be equal to what? Must be equal to 0. Understood? So what I am going to do here is I am going to follow the same procedure here. Whatever I have followed in Gauss law, superposition of Gauss law, here I am going to follow superposition of Ampere's law. That's it. Understood? Okay. So what I am going to do here is I am going to split this here. I am going to split this into what? Into into two cylindrical. I am going to split this into two cylindrical wires here. I am going to split this into two cylindrical wires. I am not drawing the total cylindrical wire. I am just drawing what? I am just drawing the circular cross sections of the cylindrical wire. Okay. So one cylindrical wire is of radius what here? Is of radius A. Okay. So I am splitting this into two cylindrical wires, right? Okay. So and I am drawing here only the cross section of that cylindrical wires here, right? So this cylindrical wire is of radius A. It is of radius A. Okay. Plus next I am considering this cylindrical wire here. This cylindrical wire. Okay. So this cylindrical wire of radius what? Of radius B. The radius of this one will be what? Will be B. Understood? Okay. Now the current density here. So if you want, you can draw the same thing here. The same thing I have represented here in terms of cylindrical wire. So this top view I have represented here, right? Okay. So if you want, you can draw in terms of cylindrical wires also. Okay. Okay. So I am roughly drawing here. So its radius is what? Its radius is A. Plus, so this cavity I am drawing here. This cavity I am drawing. So this radius is what? This radius is B. This radius is B, right? Okay. Okay. So I have just represented the top view here. I have just represented the top view. That is cross section of the cylindrical wire I have represented, right? Okay. Okay. So now we want to determine the B field at some point P inside the cavity. Understood? So now here what I am considering here as so this I am considering as a cylindrical wire. This I am considering as a cylindrical wire of radius A and carrying a uniform current density of what? And carrying a uniform current density of Z. And here let us assume the current density here is flowing in which direction here? In upward direction, that means in Z direction. So this current density I am considering, it is in which direction? It is in AZ cap direction. I am considering. Understood? Next I am considering another cylindrical wire here. Understood? Of radius what? Of radius B. Now here I am assuming that here the current density of this one is also same. But here I am assuming that the current is flowing in which direction? Negative Z direction. So inside the cavity here, not inside the cavity. So what I am saying here is wait. So I have splitted this into two cylindrical wires. So in this manner, right? Okay. So here I am considering the current is flowing in Z direction. Z direction, and in this cylindrical wire I am considering the current is flowing in negative Z direction. Understood? So that means here for this wire I can represent it as what here? Z into what? Z into minus AZ cap. Okay, so that means the current density of this wire and the current density for this wire, both are what? Both are same, but they are flowing exactly in what? Exactly in opposite directions, So in this manner, I have split this combination into two cylindrical wires of radius A and another one is of radius B, such that it is carrying a current density of Z in which direction here? Positive Z direction. It is also carrying the current density Z, but it is carrying the current in which direction? In negative Z direction. So now what will happen here? So now if I take this cylindrical wire here, and keep it at this location, okay, so then what will happen here? If you take this cylindrical wire and keep it at this location, then what will happen? See, already here the current density is nothing but what? Z, and it is pointing in positive Z direction, and for this one the current density is same, that is Z, but it is pointing in negative Z direction. So whenever I place this one here, so here already plus J is present. Due to this one, you are going to get what? Same current density that is flowing in opposite direction. So what will happen here? The net current in this region will become equal to what? Will become equal to 0. Understood? So then this one and this one will become same or not? So this is inside cavity here. Inside the cavity, the net current must be equal to 0. So what I am going to do here is, if I take this cylindrical wire and keep it exactly at this location, then already here plus J is flowing along positive Z direction, and for this one the J is flowing in negative Z direction. That means both are flowing in opposite directions. So the net current will become what? The net current will become equal to 0. Then this one and this one will become what? Will become same. Yes or no here? Okay. So I hope you have understood this one here. Right? Okay. So it is same as what here? It is same as previously we have seen now, charge distribution. Okay. So instead of charge distribution, here we are having current distribution. That's the only difference. Right? Okay. So there we have considered rho V for one sphere we have considered rho V positive, and for another one we have considered rho V negative. Understood? Okay. Okay. Yeah. So now. Okay, so now we try to determine the field, the magnetic field inside the cavity, that is at point P. So now this point P is lying inside what? Inside this cylindrical wire of radius A or not? Yes or no? So just locate this point P in this diagram here. So somewhere here. So somewhere here at point P. Understood? Okay. So this is point P. So now this point P is also inside what? Inside this cylindrical wire of radius what? Of radius B. So this point P is also inside what? Inside the cylindrical wire of radius B. So this point is present somewhere here. Okay. So at this point P, you have to determine what? You have to determine the magnetic field. So what I will do here is, I will determine the magnetic field due to this current carrying wire at point P, and also I will try to determine the magnetic field due to this current carrying wire at point P. So then I am going to add up these two. Yes or no? See, if I take this one and keep it exactly at this location, then this diagram and this diagram will be what? Will become same. Understood? Okay. So just I have splitted this into two cylindrical wires of having the same current density, but they are flowing in opposite directions. In that manner I have split these two. In that manner I have split this diagram into two cylindrical wires here. Okay. So this one is equivalent to what? Is equivalent to this one. Understood? Okay. Now try to determine the B field at this point P due to this cylindrical wire, of radius what? Of radius A, and try to determine the magnetic field at point P due to this cylindrical wire of radius B. So we know already the results or not? Yes or no? If you are having a cylindrical wire carrying a current I, then what is the B field inside the cylindrical wire and what is the B field outside the cylindrical wire? So all these things we already know. Understood? Okay, so here this point P is lying inside this cylindrical wire 1, so let us consider this as 1, and the same point P is lying inside the cylindrical wire 2. Understood? Okay, so what is the expression for B field here? What is the expression you are going to get? Tell me. What is the expression for B field inside the wire? Tell me. So B is equal to what? B is equal to, so here I am representing with B1 here. So B1 is equal to what? B1 is equal to mu I R divided by what? Mu I R divided by what you will get here? 2 pi rho square, right? Okay, so this is the expression we got inside the wire here, inside the wire. So this point P is present what? Is present inside the wire, right? Okay, so B1 is equal to mu I R by 2 pi rho square, and what is the direction here? The direction is A phi cap, right? Okay, next for this one here, so this point P is also lying what? Is also lying inside what? Inside the wire, So if the point is lying inside the wire, then what is the expression here? You are going to get the same expression, yes or no? Okay, wait. So the distance here, sorry, I forgot to represent the distance. So let us say the distance from the center to this point P is R1. Let us say this is R1. So then this will become what? Mu I R1. So this is at point P here, So that is inside the cavity. We got B1 bar is equal to what? Mu I R1 by 2 pi rho square A phi cap. Now similarly at point P, right? So what is B2 bar here? What is B2 bar? Tell me. So let us say the distance from here to here is R2 here. Okay, so B2 bar is equal to what? B2 bar is equal to mu I R2 divided by what? Divided by 2 pi rho square A phi cap. So this is the expression for B field. Inside what? Inside the cylindrical wire. So these expressions we know here already, right? So in order to get the net magnetic field, what you have to do? You just add up these two B fields. Then you are going to get what? You are going to get the net magnetic field at point P. So that is inside the cavity. Understood? Okay. Yeah. Now see here. Okay. So I am copying these expressions here, right? Wait here. Wait. See here, consider the current. Here consider the wait here. So here instead of writing the expression in terms of I, so write the expressions in terms of J here. Then it is going to be very simple for us. Okay, so write down the expressions in terms of I. Instead of writing in terms of I, just write down the expressions in terms of J. So inside what? Inside the cylindrical wire. Okay, so what are the expressions we are having here for inside the wire in terms of J? Because they have given in terms of J, yes or no? Current density. In terms of current density, they have given the problem. So I am trying to write in terms of J only. Okay, so inside the wire here, this is the expression we are having, right? So mu J R divided by what? Divided by 2. Okay, so B1 is equal to what? B1 is equal to mu J R1 divided by what? Divided by 2, right? And B2 bar is equal to what? B2 bar is equal to mu into J R2 divided by what? Divided by 2. Mu into J R2 divided by 2 A phi cap. Okay, so I have just written in terms of what? Instead of writing in terms of I have written in terms of what? Z, because they have given in terms of what? Current density, and here also we have considered the current density is in which direction here? Az cap, and here also we have considered, we have represented in terms of current density. So I am representing the expressions in terms of current density here, right? Okay, okay, yeah. So now I am copying this here, I am copying these expressions, right? Okay, okay. Okay, so B1 bar is equal to mu J R1 bar R1 by 2 A5 cap, and B2 bar is equal to what? Mu J R2 bar by mu J R2 by 2 A5 cap. Wait. Okay, see here, one thing you have to understand here is, see here, let us assume z-axis here, let us assume z-axis is coming out of the board here. Here z-axis I have taken in this manner, so just consider the top view. Okay, so like this, if you tilt like this, so here you are seeing the cross section, and z-axis is coming out of the board, z-axis is coming out of the board. So let us assume z-axis, let us assume z-axis is coming, let us assume z-axis is coming out of the board here, let us assume z-axis is coming out of the board, right? Okay, so z-axis is coming out of the board, z-axis is coming out of the board, let us assume, right? Okay, so now here the current density is pointing in which direction here? The current density is pointing out of the board, yes or no? It is pointing in Az cap direction. So if the current is flowing out of the board here, if the current is flowing out of the board, then what must be the direction of B field? So the B field is going to circulate in anti-clockwise direction, it is going to circulate in anti-clockwise direction. That means here the direction of B field will be in which direction? A5 cap direction, yes or no? So here I have considered the current density is pointing in which direction? Positive Z direction. So if the current is flowing in positive Z direction, then the B field is going to circulate in which direction? The B field is going to circulate in anti-clockwise direction. That means that the B field will be in which direction? A5 cap direction. Understood? Now here what we have considered here, the current density or the current is flowing in which direction? Negative Z direction. It is flowing in negative Z direction, yes or no? So if the current is flowing in negative Z direction, so that means okay, so okay. So if I represented z-axis coming out of the board, means you have to understand that negative z-axis will point into the board. Understood? Okay. So here the current density is in which direction? The current is flowing in negative z direction. So if the current is flowing in negative z direction, that is into the board. So if it is pointing into the board, then what must be the B field here? What must be the B field direction? So the B field is going to circulate in which direction? In clockwise direction. That means it is circulating in which direction? Minus A5 cap. Okay, so anti-clockwise we will consider as plus A5 cap. If it is clockwise, if it is circulating in clockwise, then you have to consider it as what? Minus A5 cap. Understood? Okay, so here A5 cap, it must point in which direction? Minus A5 cap direction, right? Okay, why here? Why? Because here we have considered the current is flowing into the board. If the current is flowing into the board, then the B field is going to circulate in clockwise direction. That means in minus A5 cap direction. Understood? Okay. Or if you want, you can check here. Or if you want, you can check here. Here the current is flowing in upward direction. Yes or no? Okay. So that means the field is going to circulate. In anti-clockwise direction. That means in A5 cap direction. So for this wire, the current is flowing in downward direction. Yes or no? That is in negative Z direction. If you consider this one here, right? Okay. So now here the B field is circulating in which direction? The B field is going to circulate in clockwise direction. That is in minus A5 cap direction. Understood? Okay, so if you change the direction of current density, what will happen? The direction of B field is also going to change. Okay, so here B1 is pointing in which direction here? A phi cap direction. So initially we just written the expressions, that's it. Okay, now we are taking the directions of currents, and hence we have to consider the directions of B field also. Understood? Okay, so for B1 the direction of B field is along A phi cap direction. For a B2 the direction of B field will be in which direction? It is in minus A phi cap direction, right? Okay. Okay, yeah. So here you have to write here, it must be in which direction? Minus A phi cap direction, right? Okay. Now now in cylindrical coordinate system, we know that aero cap, what are the unit vectors here? Aero cap, A phi cap and AZ cap. So this is radial direction, and this is circular direction, and this is what? This is along Z direction. This is along Z direction. Understood? So we know this one here. Now see here. Now here we have considered Z is okay. Aero, A phi, AZ. Now here A phi cap I can represent it as what here? Tell me. Here I can represent A phi cap as what? Tell me. How I can represent A phi cap in terms of aero cap and AZ cap here? How I can represent? I can represent A phi cap as what? AZ cap cross what? AZ cap cross aero cap will give you what? A phi cap. Okay. So A phi cap I can represent it as AZ cap cross what? AZ cap cross aero cap. AZ cap cross aero cap. Understood? Okay. So why I am doing all these things, you will get understood soon, right? Okay. Okay, yeah. So this is equal to mu into J into R1 divided by what? Divided by 2. A phi cap, you can write it as what? You can write it as AZ cap cross what? AZ cap cross aero cap. AZ cap cross aero cap. Now see here. So I am writing this one as mu by 2. I am writing this as mu by 2 into J AZ cap. I am writing J AZ cap. Just I am multiplying with J here. Understood? So cross what? Cross R1 aero cap. Can I write in this manner here? Now you can take J outside, R1 outside, then you are going to left the same expression or not? You are going to get the same expression. Understood? What I have done? I have just multiplied J with AZ cap, and I have multiplied R1 with what? With aero cap. Understood? Now if you observe here, if you observe here, J current density is pointing in which direction? AZ cap direction. So J into AZ cap, I can write it as what? I can write it as simply J bar. Okay. Now, okay, J bar. Next, this R1 here. So this R1 is nothing but what? Is nothing but a radial distance. Yes or no? This is the radial distance from the center of what? From the center of the cylindrical wire. So that means this R1 is along which direction here? This R1 is along which direction? Is along aero cap direction. This R1 is along aero cap direction. Understood? Okay. So that means R1 aero cap, you can write it as what? You can write it as simply R1 bar. See, this is a radial direction, and this is nothing but what? This is nothing but along phi direction, and this is nothing but what? This is along Z direction. Understood? Okay, you have to remember cylindrical coordinate system, right? Okay, yeah. Now now that means here J AZ cap, I can write it as what? I can write it as J bar cross what? Cross R1 aero cap, I can write it as what? Simply R1 bar. So this is the B field. At what? At point P, due to what? Due to a cylindrical wire. Of radius what? Of radius A. Right? Okay. Okay, yeah. Next. Now in the same manner here, for B2 bar. Okay. Okay, so in the same manner for B2 bar, how you can write here? So B2 bar is equal to what? Is equal to mu into what? Mu by 2. Okay, I will write mu by 2 J R2. Now here minus A phi cap here. So how you can write minus A phi cap here? So A phi cap is nothing but AZ cap cross aero cap. Minus A phi cap means what? Okay, or otherwise okay, so you keep minus as it is here, so A phi cap you just write down AZ cap cross what? AZ cap cross aero cap, right? Okay, so this A phi cap I am writing as AZ cap cross aero cap, so I am just placing the minus sign as it is. Understood? Okay, yeah. So now B2 bar is equal to what? Is equal to mu by 2 into what? Into J of minus AZ cap, cross what? Cross R2 into what? R2 into aero cap. So in this manner I can write. Yes or no here? Okay, here. So just I have multiplied J with a minus AZ cap and R2 with aero cap, right? Okay, here. Okay. So this is equal to what? This is equal to mu by 2. So here J AZ cap we have written as what here? J bar. So J into minus AZ cap, you can write it as what? You can write it as minus J bar. Yes or no here? Okay. So what is the difference between for a bigger cylindrical wire and a smaller cylindrical wire? What is the difference? So the difference is only in the directions of what? In the directions of current density. Yes or no? So here if it is flowing in positive AZ cap direction, here it is flowing in what? Negative AZ cap direction. So this J AZ cap I can write it as what? J bar, and here you are having minus. So minus J bar cross what? Cross this R2 aero cap, I can write it as what? I can write it as R2 bar. Right? Okay. So this is equal to what? So therefore you are going to get what? Therefore you are going to get B2 bar is equal to what? Is equal to mu by 2, or I can take minus common here, minus mu by 2 into what? Into J bar cross what? J bar cross R2 bar, right? Okay, so let us say this is equation 1 and let us say this is equation 2. So this is at point P here, right? Okay, so this is also at point what? At point P, right? So this is due to cylindrical wire, of radius A, and this is due to cylindrical wire of radius B. Okay, so this is a cylindrical wire of radius B and this is a cylindrical wire of radius A. Okay, so now what is the total B field? The total B field or net magnetic field. So the net magnetic field here, at point P, that is inside the cavity, is equal to what? Is equal to B1 bar plus what? B1 bar plus B2 bar. So if you do this, what you are going to get here? See, I can take mu by 2 common, right? So from this expression I can take mu by 2 common. So then I am going to get what? I am going to get J bar cross R1 bar, minus of what? Minus of J bar cross what? J bar cross R2 bar. So from here, what I am going to get here? I can write the same thing as a, see here, I can write the same thing in this manner. So mu by 2 into what? From these two I can take what? I can take J bar common. So if I take J bar common here, then I can write this as J bar cross of R1 bar minus what? R1 bar minus R2 bar. So in this manner, can I write the same expression or not? Yes or no? So if you do, you are going to get what? J bar cross R1 minus J bar cross R2. The same expression you are going to get. So the same expression I can represent in this manner. So this is the net magnetic field here. This is the net magnetic field inside what? Inside the cavity, that is at point P. Okay. At point P. Right. Okay. So now we have to identify what is this R1 bar minus R2 bar. So is there any way for us to represent this R1 bar minus R2 bar? Now see here. See this R1 bar. is nothing but the distance from the center of this cylindrical wire to this point P, and here this R2 bar. So this R2 bar here, this R2 bar is the distance from the center of wire to this point P, So that means here, if I represent here, so the distance from the center of the wire to this point P is nothing but what? Is nothing but R1 bar. I am considering this as R1 bar. And the distance from the center of this wire to this point P is nothing but what? Is nothing but R2 bar. So the distance from here to here is nothing but what? Is nothing but R2 bar. Right? Okay. So now see here. Now the distance from this center here, from this center to this center, let us say this center is O and this center is O dash. Okay. So the distance from this center so the distance from this center to this center is nothing but what? Is nothing but, they have given D. Yes or no? So let us consider that as what? That as a D bar here. Let us consider that as D bar. Understood? Okay. So from O to O dash, I have considered it as D bar, and the distance from O to this point P is nothing but R1 bar. So this distance is R1 bar, and the distance from here to here, I have considered it as what? R2 bar. Right? Okay. Okay. So now see here, we have studied that the vectorial sum around any closed path is always equal to what? Is always equal to 0. Yes or no? Now if you consider this closed path here you are having O and here you are having O dash, right? Okay. So here the vector that is pointing from here to here is nothing but D bar, and from here to here this point P, here we are having point P. So from here to here R2 bar, and from here to here we have considered it as what? R1 bar. So we know that the vectorial sum around any closed path is always equal to what? Is always equal to 0. Understood? So as you move from this point to this point here, if you are moving along the direction of the vector, take it as positive. If you are moving against the vector, take it as negative, and sum up all the vectors and equate it equal to what? Equate it equal to 0. Understood? So as you move from this point to this point, so you are moving along the direction of the vector, so you are going to get D bar, and as you move from O dash to P, you are moving along the direction of the vector, that is what? Plus R2 bar. And here as you move, okay, okay. Or okay, from O dash to P, right, and from O to P, right? Okay. Okay. So D bar plus R2 bar minus what? Minus R1 bar is equal to what? Is equal to 0. So from here, what you are going to get here? A D bar is equal to what? D bar is equal to, you are going to get R1 bar minus what? R1 bar minus R2 bar. Yes or no? Okay. So from here we got D bar is equal to what? D bar is equal to R1 bar minus R2 bar. Understood? So this D bar is nothing but what? This D bar is nothing but the distance from the center, the distance from the center of the distance between the centers of what? The centers of the two cylindrical wires. Yes or no here? So it is the distance between the centers of the two cylindrical wires. Now see here. Now if you consider some other point P here, if you consider point P here, somewhere here, so then also you are land up with the same result here. Then also you are going to land up with the same result. Understood? Okay. So if you consider the vectorial sum around any closed path is equal to 0, if I apply this concept, then whatever the point you can take, you can check here, you can check that also. Okay. So you can take whatever the point you can take inside this cavity, you are going to get what? You are going to get D bar is equal to what? D bar is equal to R1 bar minus R2 bar. Understood? Okay. So that means what here? So where this d bar is nothing but what, is nothing but a distance between what, a distance between the centers of what, between the centers of two cylindrical voids, distance between the centers of two cylindrical voids. Okay, so whatever the point you can take, inside the cavity, always you are going to get R1 bar minus R2 bar is equal to d bar here. You are going to get d bar. Understood? Okay, so that means irrespective of point here, you are going to get always R1 bar minus R2 bar as what? R1 bar minus R2 bar as d bar. Okay, that's for sure. If you want, you can check that, right? Okay, so now see here. Now see here. Now see here. Now R1 bar minus R2 bar. So R1 bar minus R2 bar you can replace with what? You can replace with d bar. Understood? Okay. So therefore the net magnetic field here, at point P, is equal to what? Mu by 2 into what? Into z bar cross what? Z bar cross d bar, where this d bar is nothing but what? This is the distance. Between what? Distance between the centers of what? Between the centers of two cylindrical wires. Distance between the centers of the two cylindrical wires. So what do you mean by this result here? What we can conclude from this result? Tell me. What we can conclude from this result? See, whatever the point you can take here inside the cavity, finally you are going to get what? You are going to get R1 bar minus R2 bar is equal to what? Is equal to d bar. So that means what here? That means it is not depending upon what? It is not depending upon R1 bar, and also it is not depending upon R2 bar. It is depending upon what? It is depending upon only a d bar. See here. See, for example, if I consider, I will take some point here. Let us assume some point here. So then the distance from here to here, I am considering this as R1 bar, and the distance from O dash to this point, I am considering it as what? R2 bar. So now also the vectorial sum around this closed path is equal to what? Is equal to 0. So R1 bar. So move from here to here, R1 bar minus what? Minus R2 bar, and here you are going to get minus d bar is equal to what? 0. So that is d bar is equal to what? R1 bar minus what? Minus R2 bar. The same result you are getting. Understood? So even though R1 is changing or R2 is changing, finally the result is nothing but what? The result is nothing but d bar. Okay, so that is the beauty of this vectorial sum here, right? Okay, so that means whatever the point you can take here, inside the cavity, so at each and every point, the magnetic field is going to depend upon only what? Is going to depend upon only d. It is going to depend only upon d. Understood? Okay, so if you increase the radius of this cavity here, if you increase the radius of this cylindrical cavity, then also you are going to get what? Then also you are going to get the same result. Or if you increase the radius of this cylindrical cavity, if you increase the radius of this cylinder here of radius A, if you increase the radius of this cylinder of radius A, or if you increase the radius of this cylinder B, then also the result is going to be what? Then also the result is going to be same. Yes or no here? It depends only upon what? The B field inside the cavity is going to depend only upon the distance between the centers of the two spheres. Understood? It doesn't depend upon the radius of this cylindrical wire A, or it doesn't depend upon the radius of this cylindrical wire B. Okay? Understood? Okay. Now for the same problem here, if I take this cavity here, if I move this hole, or if I take this cavity and keep it exactly at the center here, then what is the B field inside the cavity you are going to get? See, if I take this one and keep it exactly at the center, then what will happen here? Then what will happen? The distance between the centers of these two cylindrical wires will become what? Will become equal to 0. Yes or no? If you take this cylindrical wire and keep it exactly at the center, understood? So then the distance between the cylindrical wires will become equal to 0, and hence you are going to get B field. You are going to get B field will also be equal to what? Will also be equal to 0. So what I am saying here is, if you move this cavity such that the center of this cavity and the center of this wire, okay, both are coinciding. In that case, this D will become what? This D will become equal to 0. Understood? So in that case, the magnetic field inside the cavity will become equal to 0. When it will become equal to 0? When the centers of the two cylindrical wires will coincide with one another, then the distance between the centers of the cylindrical wires will become 0. In that case, inside the cavity, the magnetic field will become equal to what? The magnetic field will become equal to 0. Understood? So one thing you have to remember here, whether it is current distribution or charge distribution, as we have seen in Gauss law. Okay, so in both the cases here, the electric field inside the cavity is depending upon what? Is depending upon only the distance between the centers of the two spheres. Here also the same thing, yes or no? So here also the magnetic field inside the cavity is depending upon the distance between the centers of the two cylindrical wires. Understood? Okay, so that's what you have to understand here. That's what you have to understand. So if you understand all these things, the analysis is taking somewhat time here. Once you have understood this one clearly, okay, so within 1 or 2 minutes you can easily answer this question, right? Okay, okay, yeah. Just in order to explain each and everything, it is taking this much of time, but don't get scared that this problem is taking this much of time. So how we have to solve all those things, don't think like that. Understood? Okay. So once you get familiar, just I have explained each and every step, that's why it has taken this much of time. Okay. For the analysis, it has taken this much of time. Understood? So once you get familiar with this analysis, once you have understood this one, then you can easily solve this problem within 1 or 2 minutes, right? Okay, so that means okay, so here you can write a special case here. You can write a special case. Okay, so now here, if suppose in the same problem they have given a cylindrical wire of radius A, and now if you place another cylindrical wire, of radius what? Of radius B. Understood? So that means here this is nothing but what? This is nothing but cavity here. Let us consider this is cavity. Okay. Now in this case, since the centers of two cylindrical wires is coinciding with one another, in this case the distance between the centers of the two cylindrical wires is equal to 0, and hence whatever the point you can take here, whatever the point you can take inside the wire, what you are going to get here, this D is equal to what? Now this D is becoming 0, and hence you are going to get what? You can directly write B field inside the cavity is equal to what? Is equal to 0, is equal to 0. Okay, whatever the point you can take here, whatever the point you can take inside the cavity, everywhere B field will be equal to what? Everywhere B field will be equal to 0. Okay, whether you increase the radius of this cylindrical wire B, or if you increase the radius of this cylindrical wire A, it doesn't matter. So the B field inside this cavity will be equal to what? At each and every point it will be equal to 0. Okay, so this is special case here. You can note down this one also. Okay, so this time they may ask you the question in this manner, right? Okay, okay, yeah. So I hope this problem is crystal clear here. I hope this problem is crystal clear, right? So if you would have followed that Gauss law, then you will understand it in a crystal clear manner here. Okay, so now also I have explained each and everything. I hope you have understood clearly. I hope so, right? Okay, so now answer this question here. Second question: a hole of radius B is less than A is now drilled along the length of the wire at a distance D from the center of the wires as shown below. So the magnetic field inside the hole, that means the magnetic field inside the cavity, in this case they are saying that uniform and depends only on D. See, whatever the point you can take, inside the cavity, at each and every point, what is the expression we got? B field is equal to what? Mu into what we got here? Mu into Z bar cross what? Z bar cross D bar divided by what? Divided by 2. Understood? Okay, so it doesn't depend upon what? It doesn't depend upon radius A, it doesn't depend upon radius B, it is depending only upon the distance between the centers of the two cylindrical wires, and at each and every point inside the cavity, the B field value is going to be same, since J is constant. Yes or no? J is same, mu is constant, 2 is constant, D is what? You are not changing D, so D is also constant. So that means B field is uniform or constant inside the cavity. Understood? Okay, so uniform, the magnetic field inside the hole is uniform and it depends only on what? It depends only on D. So that means as you change the distance between the centers of these two cylindrical wires, then only this magnetic field is going to change, otherwise it doesn't change. Understood? Okay, next. So option A here, option A is correct. Option A is correct. Now in option B they have given that uniform and depends only on B. So that means they have given uniform. Uniform is correct. Uniform is correct. But what they have given, it depends only on B. So that means it is depending only on the radius of the cylindrical wire. Cylindrical wire. This one here. So that is what? That is wrong or not? It depends only upon the distance. So this is wrong. This is wrong. So and hence option B is wrong here. Right. So here they have given uniform and depends on both B and D. So it depends only on D, but it doesn't depend upon what? It doesn't depend upon B, right? Okay, so uniform is also correct. It depends only on D is also correct, but they have given another one, that is it depends on both B and D. So it doesn't depend upon B, and hence this option C is also wrong. And in option D they have given that magnetic field inside the cavity is non-uniform. So that means it is vary from one point to another point. That's what they have given here. But we have seen that it is not going to vary from one point to another point inside the cavity. Understood? So it is uniform. So it is not non-uniform. And hence option D is also wrong. So what is the correct option here for this question? Option A is correct. Option A is correct. Right? Okay. So I hope this problem is crystal clear here. I hope this problem is crystal clear. Right? Okay. Okay. Here. Okay. Right. Okay. Nitin Bhatia, thank you. Thank you, Nitin Bhatia. Okay. So I hope this problem is crystal clear here, right? Okay. So next we try to determine the B field inside a solenoid here. If you are having a solenoid of infinite length, if you are having a solenoid of infinite length, if you are having a solenoid of infinite length, then we try to determine the B field inside the solenoid. Inside the solenoid, what is the B field inside the solenoid? Okay, so this problem I will take in the next class here. Okay, so it will take hardly 15 minutes here, 15 to 20 minutes maximum. We can complete this, right? Okay. So we try to determine B field inside what? Inside the solenoid with the help of what? With the help of Ampere's law. With the help of Ampere's law, right? Okay. So we try to solve this problem tomorrow. So it will hardly take 15 to 20 minutes. Okay. So once we complete this problem, so tomorrow I am going to start time varying fields here. I am going to start time varying fields. Okay. So that means up till now we have studied about electrostatics as well as what? We have studied magnetostatics, right? Okay. So now we are going to enter into what? Time varying case, time varying fields. Understood? So that means tomorrow I am going to start Faraday's law here. Tomorrow I am going to start Faraday's law, right? Okay. So once we complete Faraday's law, okay, so it may take I am expecting within 3 to 4 days, 4 days or 5 days maximum, we can complete Faraday's law. So then after that I will take modified Ampere's law here. After that I will discuss modified Ampere's law. After that I will discuss modified Ampere's law. right? Okay, so this 2 will come under what? This 2 will come under time varying fields here, time varying fields. Okay, so once we complete these two here, once we complete these two, so then we will enter into what? We will enter into uniform plane waves. Okay, so here here we will see how we are getting how Maxwell has predicted the existence of electromagnetic waves. All these things will we can easily understand once you understand this Faraday's law and modified Ampere's law, right? Okay, so here I will try to explain most of the applications of Faraday's law, so that most of the electrical students will get benefited, right? Okay, so whatever you are studying in your machines, right? Okay, or not only machines here, so you can take any other subject like circuit theory or analog circuits, whatever the subject you can take. Okay, so for each and every subject the base of each and every subject is present in EMT here. Okay, Ohm's law is from EMT only, KVL we get from EMT only, KCL we get from EMT only, continuity equation we get from EMT only. Understood? So all these applications, all the applications of this EMT is nothing but other subjects here, right? Okay, so this is a very interesting and beautiful subject, but you have to understand the concepts clearly, then only you can enjoy the subject here. Okay, okay, so you must get the intuitive feeling of the subject, right? Okay, okay, so tomorrow we will solve one more problem based on Ampere's law, right? So once we complete this, we'll complete the statics part, so then we'll start time varying field. Okay, so this Faraday's law and modified Faraday's law is very, very important for electrical students here. Okay, not only electrical, EC students also it is important, but I will tell you some applications that you it will be very much useful for you in order to study the machines here, mainly machines, right? Okay, okay, yeah. Okay, so tomorrow we'll meet exactly at 4 p.m. here. Tomorrow we'll meet exactly at 4 p.m. right? Okay, okay. So with this I'm winding up the session for today. So don't miss tomorrow's session here. We are going to start Faraday's law, don't miss that, right? Okay, okay. So 4 p.m. guys, 4 p.m. right? Okay, so I hope you have enjoyed the session, right? Okay, so please share the session to as many students as possible, right? Okay, and like the session. Okay, so tomorrow exactly at 4 p.m. we are going to meet again. So until then, take care, bye bye.